things are as normal, right? So, thank you very much. Okay.
Who's that?
Sitting in there, doing this, and this. I saw it through the glass.
He's the one actually should be here first, right? For everyone else. He's working on something to show you.
Yeah, I think so.
All right, let's go ahead and then get started. So today our presenter is Professor John Lumbros from Aerospace Engineering, and I know many of you may have already taken his classes, or if you have not taken, I strongly recommend to go ahead and then take his class. He's an expert in fracture mechanics, and he teaches this topic in a very, very good and excellent way. So I really enjoyed when I was taking his class and fracture mechanics. He teaches, I think, 2 fracture mechanics classes, and I strongly recommend you, if you want to learn more about this area, I mean, that's the class that you should take from in this department. And his talk today will be about a very interesting topic, the use of X-ray tomography to investigate the particulate composite materials. So I will let him start his presentation after a warm round of applause.
Thank you.
Thank you. Thanks very much. Thank you, Hassan. The class is this fall, by the way, right? So you still have time to register. Now is the time to register. And it's a civil engineering class as well, for those of you that are interested. So thanks very much, Hassan. Thanks for the invitation to come over and give this presentation. And it actually kind of gave me also an opportunity to sit back and think about the topic of particulate reinforced composites in general. And in doing that, I kind of pulled together many things that we've done over a period of years from various different angles, but they all kind of fit under this general umbrella of particulate composites. So what I'm going to be presenting here is work by a lot of contributors, and I've listed them here. Many students and postdocs, some from UIUC, like Dr. Gates, Gonzalez, Martinez. These have all been my PhD and master's degree students. We collaborate a lot with people here at material science, computer science, aero, and we also have a collaboration with a group at the Imperial College in London, these 2 folks over here. So even though all these sort of collaborations and projects started out individually, they kind of all mesh together under this general topic of particulate composites. Particulate composites are very widely used in a lot of applications, and this is since this is in the transportation context, I kind of have a slide here where the first application is transportation related. This is from work that we have done over the recent years with Hassan and Professor Al-Qadi and a number of other students in civil engineering, in aerospace engineering, looking at fracture of asphalt concrete, which is in essence a particulate composite, and it's a particular composite of special interest because there's a very large mismatch between the very hard particles or reinforcements and a very, very compliant matrix. And what we've done, what people do in general, we have done this work, others do similar work and so on. We can look at the strains that develop in this type of highly inhomogeneous microstructure, and basically you see a very, very inhomogeneous strain field. These are what are called digital image correlation measurements on the surface of a fracturing piece of asphalt, and then the red areas basically show you where you have high strains, and this is there's a starter crack in here. But in addition to these type of civil engineering applications, there's certainly plenty of applications in the aerospace side, and this is kind of where I started coming into this area. There are aerospace applications that involve engines. Particulate composites are used in CMCs, in ceramic matrix composites. There's lots of long fiber polymer matrix composites in aerospace applications as well, right? But I'm not going to talk about that today. I'm going to concentrate on particulate composites. Particulate composites are used in things like high temperature components of turbine engines. Ceramic matrix composites are very high heat resistance materials, and you add the reinforcement in there to try and increase the toughness to levels that would allow use in practice. A system that I've worked with a bit, very similar to the asphalt in some sense, in the sense that it consists of very hard particles and a very compliant binder, are things like solid propellants. They used to be for many years here. For about 10 years, there was a DOE ASCII center in here, which we used to call the rocket center, that dealt with the simulation of the burning of solid rocket propellant. So they dealt with a multi-physics simulation of the three-dimensional combustion and eventually generation of gas products that would propel the rocket forward. So this was a very highly complex simulation framework. And one of the issues that they suffered was a lack of experimental data that would allow them both, so experimental data they could use both as input to these simulations and also to use them to validate the results of the simulations that you would get at the end. So even though the simulation could be extremely fancy, have three-dimensional multi-physics capabilities and multi-scale capabilities and so on, if the correct experimental information is not there, then that could certainly lead to problems. Explosives are also very similar to propellants. They're actually more or less the same thing, only explosives have a much higher volume fraction. Explosives might have a 95% volume fraction of the hard particles. The hard particles are the ones that actually explode, right? The chemically reactive particles, whereas rocket propellants may be about 65%, which would be something that would be similar, let's say, to asphalt. But there's also, there are other systems as well that have this characteristic of a distribution of hard particles in soft matrices, and that are of interest in aerospace engineering, in civil engineering, and other industries as well, such as, for example, self-healing composites. There is a large group in aerospace engineering that deals with self-healing composites, where, for example, you might have these glass particles that would be filled with a polymer that when they break, they would heal the composite. And we've done a lot of work in this system as well, and I'll show some results on that. Again, a very similar system of hard particles in a compliant matrix are battery electrodes. So modern or newer battery electrodes have a design that tends to be like this, where you would have these round particles are meant to be host particles that will host the electrically active material. In this case, in most cases of what you have in cell phones and computers and so on, that would be lithium ions, right? So these are the lithium ion batteries. The lithium would reside in these red spheres depicted here, and it would transport between the anode and the cathode during charging and discharging. So there's a lot of systems that kind of motivate the study. Our work has been primarily of this type, and what we've done, and similar to what we've done here with the group here, is doing image correlation on to measure, to quantitatively obtain strain fields on the surface of these samples when they undergo a variety of loading and so on. For those of you that don't know what image correlation is, just very quickly let me say, it is essentially you take a random pattern of dots, you deposit that on the sample surface, and it would look something like this. Let's say this is just a piece of paper with paint on it. And then once the deformation occurs between the initial state and the deformed state, because of either some loading, it could be mechanical loading, thermal loading, electrical loading in the case of the batteries, whatever. Something happens that changes the shape and the size of this object. You can then find this deformation by kind of tracking where these particles go to. And you don't track pixel for pixel. That's impossible to do. So what you track is actually little subsets or groups of pixels, right? So you can pick a subset.
3 millimeter or micrometer?
This is 3 millimeters, but this particular method, unlike other optical methods that are based on light, for example, interferometry methods, right? This does not have an inherent length scale. If you're using a technique that's based on light, the length scale is limited by the wavelength of the light you're using. Maybe a half or a quarter would be about the smallest you can get, right? This is a scaleless method. So if you can go to get a picture like this, and it looks the same as this, but the scale is 3 microns, then you can use this method, and people have done that. We have done that, right? So this is an inherently multi-scale method. If you can do this with this scale being 3 nanometers, great, you can use it again, right? So people have used this in an SEM, so a scanning electron microscope, a transmission electron microscope, and so on, right? That's a very important observation in the sense that depending on at which scale you want to make observations, you have to have the correct optical equipment to do this. But the methodology is the same, right? Now, it can be very difficult to get the right pattern at smaller scales. So there are challenges, obviously. But the approach would be the same. You would match a subset here and try and track where it went in the deformed state. And here, this particular subset went actually over here. And if you look at these two subsets, you can see, they're the same thing. There's a little question mark over here. There's this little U-shaped thingy over there. So this subset moved over there. So in that process of correlating, and that's why we call it correlation, correlating this subset to that one, we can actually obtain the displacement and the displacement gradients of the center point of this subset. And that's more or less how it works. I want to go into much more detail, but the only thing I'll say is that essentially your eye does image correlation almost immediately, right? So if I look at this pattern and then I look at this one and I kind of just jump between the two, so what this doing? Yeah, rotation, right? Exactly. So I see people going, this is rotation. Right? So if I run the image correlation, I get this as the field, and it is indeed a rigid rotation of 5 degrees with the center of rotation somewhere there. And the eye picks this up, almost immediately. Well, now we have, the image correlation is essentially an algorithm that does the same thing. The problem is the following, that it does it on the surface. And that's very good. And this is, in general, a problem of experimental mechanics. Most of the times, if you put a strain gauge or whatever, our measurements are on the surface. And that's great. We can get a lot of information from that. But we are limited, especially when we get into trying to understand what very complex materials such as this do, right? Like I mentioned, the Rocket Center, the DOE ASCII Center that ran for 10 years was trying to do a multi-physics, multi-scale, 3D, obviously, simulation of something like this. And a lot of the problems was running into a difficulty in terms of having the appropriate experimental data that will allow you to analyze such complex microstructures. Asphalt is another similar microstructure that it is highly complex, especially if you look at the third dimension. And what that means is that really we want to have some way of being able to quantify what happens in 3D. And mostly that way so far has been numerical. And what we're trying to do is to add some experimental component to that. And here's one example that I pulled from the literature. I did this a couple of nights ago, where people tried to obtain a quantitative understanding of failure in asphalt materials in 3D by starting out from a 3D microstructure, which they obtained from X-ray tomography, then digitizing the microstructure in a simulation framework, and then performing a simulation. But how accurate is the simulation, right? This is something that is not 100% clear. So we would like to be able to do a lot of these things that are typically looked at only numerically, also with experimental methods. Study damage, do things like quantifying things like representative volume elements and stuff like that. When you do upscaling of numerical techniques, this is an important concept. The RVE concept is very important. So far, again, it's something that's only been determined experimentally. And like I said, we also want to be able to, at the end of the day, be able to validate simulations, complex 3D simulations, not solely by measuring what happens on one surface, but being able to see what happens inside, right? So we would like to be able to do something like measure the 3-dimensional deformation of something, not merely the surface deformation, and we're going to do that with what we term digital volume correlation, or what I denote here as DVC, and that's what I'm going to talk about. What I'm going to talk about today. So, okay, so I went through a little bit of a background first. So the first thing that we need to do in order to be able to make these type of experimental measurements is we have to be able to see inside, right? So we have to have some way of doing 3D imaging, and I'll talk about that next, and that essentially is, what we use is X-ray computed tomography. There's a few other methods out there, not many, but there are a few others. Confocal microscopy, maybe ultrasounds, perhaps, things like that. But beyond just doing imaging, and people have used these types of imaging techniques extensively to do things like detect damage, right? So beyond that, we would also like to use them as metrology instruments, not just imaging instruments. That means getting actual measurements out of that. And that we're going to do with the DVC technique, which I will present after that. And I'm going to show you two examples. And then, like I said, these kind of came from different directions, but they sort of meshed together under this overall topic of particulate composites. The first was our initial attempt to make something that we could study that would be comparable, let's say, to something like a solid rocket propellant, a hard particle in a compliant matrix. And we made these model composites where we have hard particles, spheres, in a compliant PDMS matrix. And I'm going to talk a little bit about that. We'll look at particle debonding and then how we study particle debonding through some numerical simulations, so kind of trying to show you how these two will mesh together. The second application I'm going to show you is a more complex structure, higher volume fraction with a lot of particulates, and that is the operation of a composite electrode, where the loading will be not mechanical, but it will be electrical, as I mentioned. Right? So let me start with some of the optical methodology things. So we need to look inside, as I said, right? So the way that we do this is by X-ray microcomputed tomography. We do this at the Beckman Institute. There's a number of scanners there. This is the one that we use, the X-Radia 400. It's a micron level scanner. There is a nanoscale scanner as well. And there's a range of other ones. But for those of you not familiar with this, the idea is pretty straightforward. You have a sample through which you pass an X-ray. You have an X-ray source, and then you have an X-ray detector over here, which would just be like a camera, if you want to think of it that way, but it's sensitive to X-ray images. And this would be exactly the same sort of X-ray as you would get, when you go to the doctor or whatever. The only difference is that you rotate the sample so that you take these X-rays through a set of 360-degree angles. And of course, the smaller the angle, the higher the accuracy. But you would say, let's say every 1 degree, right? So you would get 360 images all around, and they would look something like this. This is for a sample. This is a very simple sort of model composite. A polymer PDMS matrix with a hard alumina, so a ceramic sphere in it. And you can kind of even see here how we make these, right? So we cast a little bit of the PDMS down and we let it gel, not completely. Then we just drop the one sphere in, and then we pour the rest of it out. So there's a little interface here that you can see, right? And then you take this bunch of X-rays, and this is just what would be called the 2D radiographs. So the regular 2D X-rays that you would get, if you were to break your wrist or something, as they're rotated around through 360. And then through a variety of computational tools, and we can convert this to information in the interior of the sample. We can convert it to a set of information which will correspond to 2D slices along the height, which basically would be slices like this that would show us the interior of the object. And then we can also do, and they would look something like this. And then we can also do a 3D reconstruction, which I've shown in a sec. So this is essentially the alumina sphere. This is the matrix, and you see all these little white dots in here. We have placed these white dots, and these are the ones that will be used, that will take the role of the surface speckle pattern of paint that I showed you a little while earlier for the 2D image correlation, right? So these will be the markers that will be tracked, and this is the hard inclusion meant to simulate something like, the aggregate or the explosive material in the propellant and so on. And you can see, like, for example, there's a crack in here, right? Which you can't tell when you look at this. It's just an opaque sphere, but when you put it in a tomograph, you can even see it, right? Almost all of them have cracks. We were thinking we'll send them back because they send us all these spheres. We buy them. They all have an internal crack, and I'm sure they don't even know it. So after that, we can create a 3D reconstruction, which again is the same thing if this plays. I don't know why it's not playing. Let's try again. Cannot play movie. Okay, let's see here. Does it play this way? There you go. All right, so this is now the 3D reconstruction, and of course this is the sample is cylindrical in this case, and we have internal information as well, right? So if you cut out through the thickness, then you would be able to see, and then that's the sphere over there. So along with the sphere, we have information on these additional marker particles that we've put in there, which are glass, essentially. So the sphere is, well, I'll show you in a sec. The sphere is alumina, the particles are glass. So essentially, we can perform now what would be thought of as a three-dimensional equivalent of the same type of correlation that I showed you before, only now instead of using these square subsets and try and trace where they went, we now use cubic little subsets, and we have voxels instead of pixels. Why would they hit? What do you mean hit the sample?
So X-ray has extra particles away, has energy.
You're talking about during the scanning.
Yes.
All right, not the physical contact with the particle. Scanning is performing the scanning and getting a good image is one of the most difficult parts of this. Probably the most difficult part. If you have particles and components and so on that have very high, essentially what you're measuring here is density, right? If they have very, very high density differences, then it's a problem, right? So what you're talking about is what is called shadowing, right? So if you have, for example, a metal in there, and you try and scan that like a metal particle, there will be a very large shadow, in quotation marks, that is cast behind it. So it's a shadow in the X-ray range, right? And that would be a problem because you would basically have hidden areas of the sample and you wouldn't get a very good reconstruction. So yes, having shadow artifacts, ring artifacts as they call them and so on, are all significant problems that you have to deal with, right? What I'm showing you here is what we've done to get good images. And that's why I call this a model composite. We have made it this way so that it works both with the tomograph and with the image correlation and so on. If you take a random material, it may not work exactly. Right? So you have to play with the intensity of the machine, the size of the beam, the magnification, and so on. There's a lot of things that you have to do to get the image to look proper before you can actually do an image correlation, right?
So I thought,
I think what you don't mind, let's keep the question at the end.
That's the five. I don't mind either way.
That's probably look better. Yeah.
It's okay with me, whatever you prefer. So again, we have a rotation, and then now you can kind of see this rotation, but now we pick it up in 3D instead of 2D, right? So basically, instead of having these equations, as I showed before, that would define the transformation where we would find the displacement gradients. Now we have the 3D version of these. So we can get UVW, all 3 displacements, and all 9 displacement gradients, and you get these all simultaneously and separately. So the displacement gradients are not a derivative of these displacements. They are an outcome of the correlation function. You correlate all these together, and I'll skip these details. I won't go into the correlation details. The only thing I will say is that, again, as I mentioned before, there's a lot of work that has gone behind this by a large number of people from a variety of angles, right? The computational angle is another one. One is the imaging angle, and there was a group of people working in that. A different group of people, and this is where we were collaborating with people in computer science, were dealing with the computational side. On paper, it looks the same, and basically what you're saying is, well, okay, instead of fitting these 6 parameters, I'm going to fit these parameters in here in 3D. The problem with that is that, okay, yes, in theory it sounds great, but the problem is much, much larger in size when you go to the 3rd dimension. The images are much bigger. They're gigabytes instead of megabytes. The runtime is much larger. In a typical 2D case, maybe let's say you would do 100 by 100 correlation points, and that's on the small side as well, right? We may do more than that. And that might take you a few seconds, tens of seconds at most, right? If you want a comparable density of measurement points, so the correlation points, which are the centers of these subsets, are the measurement points. If you want a comparable density in 3D, so we did 100 cubed, then again, I'd like even more of these, really. Because both the size is much, much bigger, and the computation time per correlation point is much bigger, because now you're computing over a cube and not a square subset, you end up with something like days, right? So this is, of course, not acceptable. So the way that we deal with that is we do everything in parallel. So we basically implemented a couple of different versions of a parallel computation. We started with a large number of CPUs running in parallel, and we were able to get something like 1,000,000 degrees of freedom, which is more than that, 10 times more, in about an hour, which is actually comparable to, if you want to think of it in terms of comparing to an optical experiment, it's comparable to the time of imaging, right? So your imaging takes between half an hour and an hour. So that's not too bad. But then you can actually perform a further parallelization by using GPUs, so graphical processing units, and that can accelerate the time even further. The way that we do this is, well, okay, you can look at granularity at many levels. You can do maybe, you can have a different processor doing a different image. That's we won't deal with that. But what we did when we implemented CPUs is we had different processors looking at different subsets. And then when you add in GPUs, you can have one processor and a number of GPUs looking individually within each subset. Right? And there's various other things. There's memory management and so on. I won't go through that just in the interest of time. But then eventually, like I said, what we were able to do is we were able now to run routinely maybe 1,000,000 degrees of freedom, 1,000,000 measurement points, I should say, not degrees of freedom, right? It's not a simulation. And we can perform 1,000,000 correlation points or 1,000,000 measurement points in our 3D volume in anywhere from 20 minutes to 1 hour, depending on whether we're using GPUs or not. So I won't go through too much the details of the parallelism. All right, so what do we do with this? Let me just show you a couple of applications. So first, we developed we tried to develop sort of a model system of hard particles, the system that I showed you before. And so far, everything we have is spherical particles. We have done and are doing now some experiments on other different shape particles. That's kind of a different story. In this particular case, we were interested in just sort of a simple geometry of a spherical particle that, as you progress loading, the particle will eventually debond, right? And this is the primary mode of failure that we see in things like explosives and propellants, and that's why we wanted to concentrate on that. So we started by studying the material. This is the matrix with so the matrix is this, with the small glass marker particles in it. So because the marker particles are, much stiffer than the matrix, they provide a reinforcement. So essentially what you've done is you stiffen the matrix, right? And we're going to have to take that into account. So we did a bunch of experiments on the matrix on its own. And then we include these hard inclusions, and these are the inclusions that we're interested in. They are the ones that are meant to simulate the hard particles. And we have configurations with a single inclusion, with a couple of inclusions, and then more than that, right? So a handful and then many. And I'll show you all of these examples. But these are the ones that we have the most results for. And then what we do is we take the sample and we put it inside the tomograph in a load stage, right? So there's a load stage. This actually is, initially, we didn't have one of these load cells. We built our own. So we built an in-house custom-made load cell, which we would put in the tomograph at Beckman. Then more people were interested in using it. So then at some point, they actually bought, the company came out with an off-the-shelf component that does more or less the same thing. And they bought that. And now we're using that. And this is it. And you can see the little cylinder in here. It's opaque, right? You wouldn't be able to see through it. It's this kind of white cylinder behind here. And the bottom portion of the load cell the load frame would provide load by moving upwards, and you can measure the load and the displacement applied globally. But we can also do, of course, our imaging internally, and that's what we're interested in doing. Going back again to your question about the pattern, there's a lot of work that has to go in to get a pattern that will work. Again, we are kind of, lucky, not lucky, but we make this work by doing a lot of studies to try and figure out what the best possible pattern is. We make the pattern because we seed the particles. Now, it may not be possible to do this in every material. And the same thing happens, of course, in 2D correlation as well, right? Sometimes we use natural features that occur in the material. If they're there and they can be used for image correlation, great. If there aren't, you have to put something in. Well, in 3D, it's not as easy. In 2D, you can paint something on the surface. In 3D, it may be a bit more difficult. So we look at things like the intensity distribution. You want something that looks more or less unimodal, same as in 2D correlation, something like this. And then this is a typical distribution of that. Then we do a lot of calibration studies and test studies, uniform translations, rotations, exactly the same sort of thing that we will go through in 2D. And this is basically a uniform translation upwards by a certain amount, 10 voxels, which is fairly large. And you can vary that, and we want to make sure that we are able to capture that. And in the process, we can kind of narrow down what, for this combination of materials and of imaging conditions, what are the best concentration of particles and size of marker particles. Rotation, here's a rotation, in-plane rotation. These are all experimental results, right? So once we're happy with that, then we do an actual straining. So this is a uniaxial compression, the simplest thing we can start with. Uniaxial compression of this line. So this is the load displacement that the device provides you with. This green line is just the polymer matrix. This is the polymer matrix with the 30 micron glass particles, so the markers. It does get stiffer, right? So it does go up here. And on this material, here's results of a uniaxial tension test. This is the vertical displacement W, so in the direction of loading. It's basically straight uniform contours all around, exactly as it should be. Strain is uniform all around, right? So these strain plots, and you're going to see a bunch of these types of plots from now on. These are basically slides. So when you have very large amounts of 3D data, like finite elements, one of the problems is how do you display it, right, to be able to tell a story. So you'll see plots like this where basically you have these slices along three directions that kind of give you some flavor of what's inside. And here, the field is uniform, so it's all blue, more or less constant strain. But we have multi-axial information. Again, we have all the displacements, UVW, all the strain components. We can measure things like Poisson's ratio. We measure 0.485. 0.49 is the theoretical value. And on most of these quantities, the strains, displacements, Poisson's ratios, things like that, we are well within 1% of the thing, right? And in the process, we also get the properties of the reinforced matrix. So the next thing to do is to apply loading on this type of configuration, right? This sphere. And so this is just one sphere. Again, you can see the sort of this haze are all these particles that are in there. And then we're going to apply compression this way. And what will happen is initially, well, the whole thing will just contract. But then at some point, there will be some debonding that happens around the sphere, and that's eventually, this interfacial debonding is eventually what we want to measure, right? So with the sphere in there now, this is a single inclusion experiment. This is the load displacement, loading, unloading, and basically you can see these points marked 1, 2, 3, 4, 5. At each one of these points, we stop the loading and we perform a scan. Scan, as I said, takes about 45 minutes or more. Right? Well, it depends on the parameters, anywhere from 20 to 60 minutes. So the sample is sitting there under load at this time. The relaxation has always been a concern. There's a little bit, there's not much actually, so we were actually pretty happy to see that this combination doesn't relax too much, right? So you can see a small load drop each time, and this is the relaxation while a scan is being taken, and everything is done in situ. And once the scan is completed, then you keep on loading. So here's some selection of these scans. So point number 3, which is this point up here, so this point of the loading, more or less nothing has happened. You basically have an elastic response. So these are slices going up like this, right? So I'm showing you the 2D slices moving up. This is more or less roughly the equatorial plane. Nothing is happening here other than straining, which we can measure because we now have all the particles around, right? At location 4, which is up here, you start seeing what we term partial debonding, and it just went away. It kind of just went away. Did I flip these movies around? Well, let's play this one. No, that's fine. That's better. So over here, you can kind of see over in this region, there is some debonding. In this region, there isn't. So, and that's very difficult to control. In theory, if everything is completely axisymmetric, the first place that this is going to debond is going to be at the equator, and it should debond everywhere all around the equator at the same time. Well, that doesn't happen, right? It starts from one side, and then it kind of grows around. But at some point, as load goes up, then it does completely debond, and here's a picture of complete debonding, and here you can see it far more clearly, right? So, and this is more or less roughly the equatorial plane, and you can see now the debonding has reached all around, and then starts spreading up and down around the sides of the sphere. And this is a 3D reconstruction of this state number 5. If the thing plays, well, it doesn't want to play. Well, I won't go out to show it. You just see the same thing just rotating around. But you can see the debonding here, right? So you can see this little, and I don't know if you can see it way in the back, but it's pretty visible that you see this sort of debonding all around roughly the equatorial part of the sphere. And this is sort of the imaging quantification of damage. But like I said, we can now do metrology because we have all these particles in place. So we can actually measure the displacement field. And this is at point number 2, which is before debonding has happened. And this is the displacement field. We have a very large number of correlation points, 160,000 correlation points, meaning 160,000 measurement points in the entire volume. I'm not showing you that. This is every 10th or something. I don't even remember. It's a very, very small subset of the amount of data we have. So these are not finite element simulations. They may look like it when you plot them, but they are experimental measurements. So this is the quiver plots that show you the entire displacement field, and you can get contour plots and so on. So these are similar to the contour plots I showed you before. They're displacement, not strain, but now it's varying. So basically, they kind of we just kind of move through slices in here, through here. And then if you see, there's a little. Let me run it from the beginning again. So this one is at stage number 4, which is the partial debonding, and it may be difficult to see there from the back, but you can actually detect that there's a little bump in the displacement contours near where the debonding is, right? So we can measure this type of information both before and after debonding. Okay, but then how good is it, right? So, I showed you the tension test. We had some measurements for that. We know the Poisson's ratio, so we could establish a reasonable amount of accuracy, something like 1%. So what could we do here? Well, the reason that we made this sample, and this is why we wanted a very, very stiff ceramic in a very compliant polymer, was because there exists an analytical solution for this problem. For a rigid sphere in an elastic matrix, infinite, not finite, right? So ours is finite, but the sphere is a bit small. The spheres are anywhere from 500 microns to a millimeter. and the width is up to, I don't know, 15 or 20. So we're going to have to go with the infinite solution. So there is a solution by Goodyear from the 1930s of a rigid sphere under uniform tension or compression. Right? Compression would just be minus T, same thing. And this is the solution. I'm not going to go through it in detail, but we have it. And these are the two displacements. And T is the applied tension, which we have. So taking the external load and putting it in this solution and the material properties, which we also have for the strengthened matrix, right? The matrix with the glass particles, we can actually obtain a theoretical prediction and compare that with the experimental measurements. And I don't know if you guys can see it back there. But anyway, bottom line, they compare very, very well, extremely well before debonding, right? This is a rigid inclusion, perfect bonding. It's a simple elasticity solution. If you look far enough away from the sphere, and here this is the U displacement, this is the V displacement, this is the W displacement. This is far away from the sphere, and this is at the equatorial plane. And the solid lines, which are also wiggly, are the experiments, and the dashed lines, which most of the time you can't see because they're behind the solid lines, are the theory. They are, of course, much smoother, but they agree very, very well. First of all, far away, you just get uniform tension or compression, right? So you just get parallel contours either way, whatever you look. Near the sphere, of course, these are distorted because of the presence of the rigid sphere, but all of them agree fairly well. Even this one that has the smallest magnitude, they all agree pretty well with, so the smaller the magnitude, the higher the signal to noise ratio, right? But they all agree very, very well with the theoretical solution. So this is this displacement field, right, that we're comparing. So this was very encouraging, and basically was, for me at least, it was what convinced me that, okay, things are working, right? The problem is that this doesn't work once debonding starts. And in fact, if we make this comparison once debonding starts, the contours don't lie on top of each other. But that's the case that we would like to study. This is the important case in things like propellants, like asphalt, concrete, and so on. What you want to see is, well, how the response or how the strength of this composite evolves as these particles start debonding. And the more particles there are, the more they would debond. So this we studied numerically with collaborations with a group at Imperial College whose background is in the study of PBX and HMX explosives. So first we started by determining a model for the matrix. One thing that I haven't told you so far is that there is a bit of scatter in these results, right? So not every experiment is identical. There's a little bit of a spread. This is kind of representative of a spread of the stress strain response of just the matrix on its own. So no marker particles, no reinforcement, nothing. So basically what we do is we kind of take an average curve, which is this light blue one if I remember, and basically we fit a standard nonlinear elastic material to it, the Mounier-Rivlin material, and we determine these constants, and that actually matches pretty well, right? So this is our analytical model for the nonlinear elastic PDMS material. But then we add in the marker particles, so this stiffens the thing. We've seen that before. I showed you the load displacement curves before, and that we do essentially, we handle that essentially through a concept of what is called the representative marker element, similar to a representative volume element, where basically you have individual elements that are made up of the correct volume fraction of a stiff phase and a hard phase. We're not modeling the millions of glass particles that are in there. We just consider a sort of representative volume element of the correct volume fraction, and we consider up to 100 of these. We actually did a lot more, okay, up to 1,000, or I think it was 10,000 was the highest. But even with just 100 of these what I call representative marker elements, and this is a pretty well-established technique, you can actually match pretty well the response of the matrix with the reinforcement particles, right? So fine, so now we have that. And then, so what we did is we started doing some pretty elementary numerical simulations, and I don't know how much of this you can see in the back. This is the single particle inside the matrix. This assumes perfect bonding, so there would be no debonding. There is debonding in the experiments. And this is just a contour of some of the simulation results. This is the displacement in this direction. And you can extract from that things like displacement along here, and that's what these lines are for the various loading steps, what I had 1, 2, 3, 4, 5 before, what I showed you. And then in 4 and 5, which are these two, there is debonding, And so before they kind of match to begin with, we knew that anyway because we're matching the Goodyear elasticity solution. This also matches the elasticity solution when the thing is not debonding. But what happens when it's debonding? Well, if you assume perfect bonding, then, and it's maybe far to see from the back there, but very near the sphere, they do not agree, right? Which is kind of what we expected. We would like them to agree, so we have to somehow model the failure, so we model it with a cohesive failure process, right? So a process which would basically say that so we know that the failure is happening at the interface. We're not going to deal with failure in the matrix or the sphere. The only cohesive elements that would be placed would be around the sphere. These would basically allow softening of this bond between the matrix and the sphere once some critical stress is reached, right? And basically these types of cohesive elements essentially say is that failure is not instantaneous where the thing just snaps, but it's a gradual process that takes some time to complete, during which time the material is softening or losing resistance as you're increasing the displacement. Then at some point, if these two material points separate far enough, and that's this delta max, then they have no influence with each other, and then you have complete failure, right? So this traveling along this curve would represent the failure process. Reaching this point would represent the formation of a new crack. So the question is, what are the correct properties, right? So, and that's basically what we're seeking to do. We haven't done that yet. We are looking at a sort of a rigorous optimization process to do that. We can guess some of them. So here's a simulation of, we picked what would be reasonable values. So here's a simulation of the same thing that I showed you before. The sphere is down here, by the way. I didn't mention that, right? So the sphere is here. This is the entire sample. So the sphere is down here. It now has cohesive elements with basically strength and toughness that are reasonable values, but they haven't been fitted yet. And this is the point at which we are now. But now you can see this is a close-up of the sphere. So this would be the sphere surface. Now you can see that we do allow the formation, the spontaneous formation of a crack in this simulation. And of course it happens. It starts here exactly the same as the experiments, and it propagates up the sphere. And one way in which we're trying to optimize, when I say optimize, I mean find the actual properties of strength and toughness, right? So one way in which we're trying to do this is by comparing, what I plot here is the opening displacement of this cracked region, right? So this is the more the load you put, the load is applied this way. The more load you apply, the more that this thing is going to open up, right? And these are finite element measurements. So from here, and you probably can't see it way back there. This is for a compression of 3.75 millimeters. This is a compression of 4 millimeters, and you could have the whole range, right? Like I showed you before. So what we would like to do is compare this measurement with what we get in the experiments. And that is something that we can actually obtain and measure in addition to displacement fields, right? So load displacement would have to match, displacement fields would have to match, and also things like this, like the failure profile would have to match. This is the same thing I had from the slide before. We can actually isolate from the, if this plays, I don't know if it's going to play or not. Well, maybe not. Where is it? It is basically this one, I think. No, that's the last one. It's this one. Right. So we can isolate from the 3D reconstructions the region of debonding, and we do this through image processing. And basically, it is how do you replay this? And it's basically this region around the equatorial plane, right? And we can actually, in fact, get a XYZ location of this debonded region, right? And this here, I'm just spinning it in space. It's not. This is just. It just looks cool. That's all. It doesn't do anything, right? So we can extract similar type of measurements. I haven't compared them yet because they're not exactly the same experiment. So we are in the. This is still ongoing at this point. Like I said, I'm kind of pulling together results from a variety of things, right? But the idea is that eventually, once you have the correct representation of these failure properties, that these two will also match, and they're not far off, right? I mean, if you look at these numbers, this is about what is it? 1, 2, 3, about 80 microns up here. So this is about 80 microns, right? So this scale and this scale, they're about the same, but we just picked strength and toughness to make them about the same, right? That's the extent of our fitting so far. And that has to be formalized a little bit more. But the idea is that once this is determined, this should be a property that can be extended to the case of higher volume fractions. So this is the case of higher volume fractions. So now we start adding more and more particles, because eventually we want something that's closer to a realistic representation. It becomes more challenging, a lot more challenging, especially computing the volume correlation. Here's 2 particles. That's not too difficult. Here it is. And we can actually perform a pretty good correlation. Again, this is a subset of the points that we have. They're more noisier. There's things like, here you can see a really big arrow, it's just a spurious measurement in the middle of the thing. And there's more and more of these, the more of the particles you add in there. The problem is that you cannot correlate over or through, let's say, particles, right? So they have to be eliminated from the correlation. And that can be very difficult, especially when you start getting more and more particles. So with a handful of particles, we can get some sort of results. And again, these are the quiver plots of displacement. The whole thing is being squished this way. The only thing but it's not quite visible here, but I'm going to tell you, is that we have difficulty determining the displacements between the particles. And unfortunately, that's where you want them the most, right? We would really like to see what happens as these particles interact. It's probably going to be possible with this setup. So now we have a series of experiments here where these 2 inclusions are getting closer and closer together. So at some point, when they're far away, you do get the result of 2 individual spheres on their own, and then how do they interact as they get closer together? Well, that we could do. We're in the process of doing that. But getting the detailed displacement field here is a bit more difficult. And when you move to volume fractions that are more representative of something like an explosive, for example. So we're still using spheres because they're nice and they're easy to work with. We do have some experiments with other shapes, but mainly spheres are what we're looking at. So this is an initial configuration of this. There were marker particles in there. I don't know if you noticed. So I was talking at the time. But when you look at so this is the 3D representation, and then this is the 2D slices together. So as you see, as things progress, the graphics get a bit more fancy because the students start learning more and more of how to plot these things, right? There are particles in here, but we have not been able to do any correlation, and in part because of this. So this is a series of radiographs. This is the raw data, our 2D radial scans as the thing is going around. And these are concatenated throughout the entire loading period. So this is several hours of measurements, right, while the loading is progressing on a very high volume fraction composite. And you kind of already see, it's starting to bulge out, and then these things kind of at the end it fails and they all come out. So very different response. There's massive amounts of debonding here, and we have all that information. We can see the damage, but it's more difficult in this configuration to make a quantitative measurement. But this is what we would like to do in the future. These configurations, so a couple of particles and maybe a handful of particles, I think we can resolve, and we'll be able to get equally good detailed strain fields as before. These ones, well, future directions, right? Work in progress, as I said. Okay, very briefly, in the last few minutes, just a slightly different, actually maybe a completely different topic in terms of the physics of it, but fairly similar in terms of the need for measurements and the approach. Is our studies that, again, were separate, right? So from this to begin with, of composite electrodes. Electrodes that are used in high performance batteries and that we look towards to make battery performance even better. So just a very quick crash course on batteries. It may not be the thing that many of you are familiar with, even though you use them every day, right, in cell phones and laptops and so on. But essentially, they are devices to store energy and then deliver the energy on demand. And the way they do that is by storing material that can produce this electric current, in this case lithium, by storing it inside a host material of some sort and having lithium ions, which are these red dots that are represented here, moving from the anode to the cathode, for example, during the discharge phase. And while these positively charged ions are moving this way, negatively charged electrons are moving that way, and that gives you the current. That is a useful current in the machine. When these have migrated all the way to the other side, then you need to plug in, provide energy for them again to migrate back to where they came from, and in that process, again, the electrodes would actually go through here, but you need to provide energy for that, and that's the charging part, right? So if you look at the voltage of this, it would follow a discharge, so a useful phase, and then a charge, which would be recharging to its full potential. And this goes on and on and on. So one cycle would be one discharge, one charge and one discharge. So, you know, if you think of your cell phone or whatever, well, how many cycles does it go through? You charge it maybe once a day if it gets bad, right? You'd like to charge it once every 2 or 3 days. But let's say you charge it once a day, well, that would be 300 charges in a year. So, you know, 10 years of use, when no one uses a cell phone for 10 years, would be like 3,000 charges, right? So this is the type of numbers of cycles that we're talking about. There has to be a material in here in which this lithium is going to reside, and typically right now, what is in most of the batteries that you have is carbon, right, the graphite. And it can store a certain capacity of lithium, and that's what delivers the charge when it goes out. There are materials that can store a lot more, and people look to these as perhaps making batteries that might be 10 times as good as what we have now, store 10 times as much charge and last 10 times longer, right? Tin and silicon, for example, are these types of materials. There's a problem, however, and it's a big problem. And the problem is that as lithium goes into these host materials, well, it has to find the space. This is lithium ions, right? So it's atomic lithium. It has to go into this. It has to find the space to go in there. And as it goes in, it makes them grow, right? It makes them expand. And the more you stuff in there, the more it expands. And silicon expands by about 400%. And the poor thing just can't take it. So it would just go boom and explode. And after a couple of cycles, the battery's dead just because the host particles have completely disintegrated. In contrast, graphite only expands about 10%. This happens with graphite too, right? It's not a nice thing to have lithium come in. And after a large number of cycles, but it's in the thousands, the graphite batteries also die out. And typically when your battery dies out, this is one of the reasons, not the only reason. There's chemical reasons as well, but this is one of the reasons. So what we want to visualize is when we have these high capacity materials, what's the difference between the volume expansion with the graphite and these types of high capacity electrodes. So here's a graphite electrode, which is just a piece of matrix with graphite particles in it, and marker particles that we put in there. They're inert. They don't interact with the lithium. And we can do DVC on that. Here's just one cross section. This is the 3D reconstruction. So for this, we actually had to make a battery, a functioning battery, and we put that in the tomograph. So the loading here is not mechanical loading. It's just applying a voltage and cycling the voltage. And then the whole thing expands and contracts as the current goes back, the lithium ions transport back and forth. So we can measure that expansion and contraction, and here it is. Here is a measurement of the volume expansion of a graphite electrode. This is what we currently use, and it may not look like a lot because it's just a bunch of arrows at this point, and again, this is not all of them. But if you look at certain sections, well, actually the best one might be here. So if you look at this cross section, this might make it a bit more visible, right? It was fixed here. It's clamped at the bottom, and you can kind of see here now with the arrows the expansion of this whole thing. And it's roughly 2D, right? The arrows are kind of stacked. If you look at it on edge, they're all one behind the other. So it does have this kind of 2D expansion. But remember, we can also measure strains, so we can get actually internal strains in the electrode as it's expanding. And they're not different than the theoretical. They're pretty much expected. They're close to the 10% value, and the thing doesn't fail. But if we want to go to a higher capacity, that's a bit more of a problem, right? So here's one example of an electrode. Again, these are the 2D radiographs with tin particles. All of them are tin particles. There's no marker particles in here. This is just tin. Well, maybe there are. I don't remember, to be honest. This is a 3D reconstruction. Again, we can get slices. We can reconstruct the thing in 3D. This is showing only the particles. The matrix is, again, this is just through image processing. The matrix has been removed. Only the particles are in there. And we can get the initial sizes, distributions, and so on. And then we load it. Again, loading means basically just charging and discharging. So up here is the percentage of lithiation that has gone into this tin molecule. And the more tin goes in, the more of this compound of lithium and tin you have. And that is what the color contours are going to be in here, right? So now you're at about 50% lithiation. So you're halfway through the first half of the cycle. This is almost fully lithiated. And you can already see these particles. Number one, they've grown enormously. And number two, they're starting to break up, right? And the nice thing is we can actually see inside the particles as well, because this is an internal measurement. It's not just the surface of the particles that we're looking at. And now this is delithiation. It's the other half of the cycle, right? The charging part of the cycle. So we could see not only globally what's happening to the entire thing, but even within individual particles. So we can pick individual particles and look at them because we have that information, because this is truly 3D information. But we don't have volume correlation here. This is the problem. That's why we're trying to get the volume correlation to work with multiple internal reinforcements. And here's, for example, a particle that starts out, it gets lithiated. This is the external view, and this is a cross-section right through the middle. Right? And you can see how it gets bigger. This is all to scale. This is all to scale, and the colors are scaled with the content of lithium. And this is at about full lithiation here. You can see multiple cracks forming, and then it delithiates, and it can relithiate. So this cycles a couple of times. After that, it dies. But it did cycle a few times. Some particles just disintegrate completely, even on the delithiation, but generally this cycle. What didn't cycle even once was silicon. So silicon is what has about 10 times the capacity of graphite. And there is a desire to make batteries with silicon in them as host particles. So this is now silicon. They have a different shape. They're not as round now. They're like platelets. This is the form in which they are. And again, this is amount of lithiation, only now we're looking at silicon and lithium. And the problem here is because of the very brittle nature of the silicon material, it just completely disintegrates. And you'll see it in the next one. So you just see kind of this blue haze. It's almost gone. Not all of it. There are some particles here and there that we term non-functional particles that don't do anything. But generally, it is completely disintegrated. And you can look at the ones that don't disintegrate. You can measure the volume changes and correlate those with lithiation. I won't go through that much in detail. What we would like to do is to add marker particles in these types of systems and be able to get a strain field locally. We can get a strain field globally, like I showed you for the graphite electrode. So fine, we can do that. But we would like to get something like the sphere measurements that I showed you with a set of strain and displacement measurements around the circumference. And that's more difficult. So that's where we stand at this point with that part of that particular project. Right? But I kind of find it related to the composite stuff, which is why I thought it was a good thing to show here. So basically, yeah, just kind of summarizing, this is the sort of thing that I showed you throughout this presentation. We can make 3D measurements around, in these model composite systems, around hard particles in a compliant matrix, similar to many of the systems particular composite systems that people look at in terms of applications. We can do that for single spheres. We've done it successfully for multiple spheres, not for very, very high volume fractions, but still we have done that. We've been able to compare or to successfully make measurements before particle debonding and after particle debonding, and we're trying to extract now. We're at the stage of trying to find representative properties for these debondings. We do other things as well. I didn't talk about this much. I took this slide from a different presentation. We can also vary the strength of that interface, and in order to convince ourselves that we're doing it correctly, this is what we want to do. And we have a number of experiments. We just don't have the properties for them yet. You can make the bond here between the sphere and the matrix either stronger or weaker by functionalizing the sphere, coating it with things, by maybe making it rougher, so we can add roughness in here. So when we add roughness, we do get at least a modest increase in terms of load displacement strengthening. So we're wanting to be, once this works, it has to also work here, meaning that if you make the interface stronger, you have to get a larger sigma max, a larger G, and so on. And then I also showed you some results in terms of these sort of high volume fraction composites, which are again similar hard particles. Silicon and tin are very hard compared to their to the polymer matrix around them, and the same with carbon actually. And I showed you that where we can obtain DVC results globally. Locally, we can do imaging to detect failure, particle failure, but we have yet to do local strain measurements. That is kind of the next step, right? Well, I'll be happy to share those results once, hopefully, we have them, over the process of the next few years. So at that point, I'll just stop and take any questions that you might have. Thank you.
All right, now questions.
I noticed that there's still some restriction regarding the size of the sample to take the measurements. I mean, while you're loading, you have to keep it constant.
Keep what constant?
The load. So you mentioned that you apply the load and keep it there while you take the measurements.
Yes, actually, the application is displacement, right? So the displacement is Earth constant. The load drops a little bit. So we were worried it would drop a lot, meaning it would relax a lot. It's a polymer, right? It's viscoelastic. So we were worried it would relax a lot. It doesn't relax a lot. It relaxes a little. But anyway, it's the displacement that is held constant, not the load. Go ahead.
So I guess my main question is, how far in the future do you see this applied to asphalt concrete, which is sample size that we usually see higher than this? It's very viscoelastic, so probably keeping the load constant would be a higher challenge. And
Well, okay. Let me start with the second first, right? I don't think it's more viscoelastic than this. So, but even if it is, that is not the biggest challenge. I think that is something we could fix by some kind of feedback or something like that, right? So you can do some measurements and then feed them back. And you just need a more sophisticated loading machine than the very, very simple machine we had here. The bigger problem is, in terms of sample sizes, do you have enough energy of the radiation to penetrate through, right, and get a reasonable image? Certainly the machine that we're using at Beckman wouldn't be able to do that. So you would need to use a higher intensity machine, right? And you want to be able to penetrate through something that's large enough to be an RVE, right? To be representative of, well, again, I guess it depends on what you're trying to do, right? If you're trying to look at the interaction of a single aggregate with the surrounding matrix, you could probably do a geometry like this. That might work. If you're trying to do an actual, 60, 70, 80% volume fraction composite and want to get a representative set of properties, then yeah, you would need a much larger machine than what we would have here. But someone did it, right? It can certainly be done, right? That machines exist. I mean, we don't have one at Beckman. We've done some work at Argon. Argon has a very, very powerful source, right? So you can do what we do here in an hour, you can do that in seconds because of the power of the source that they have, right? So the APS line. And we've done a lot of work there. Potentially, you could use something like that. I don't know. I don't know whether people at Argon would be interested in asphalt concrete.
They also can't do that flash specimens.
So they tried.
We
You asked them.
communicated, and then they also can penetrate deep enough. For the sample sizes like we have, like one.
Well, I mean, you're showing me this. Yeah, that they could not penetrate.
Even in their facility, that kind of really.
Yes. Well, this is big. Yes, I don't think this would be anywhere, right?
Even 100 millimeter diameter, they can't penetrate. So that's just a problem limitation.
Right.
But there are places like we'll talk later. But there's some other places like in Texas. There's geological science faculty. They have, I think, a good facility. They can do large specimens. Like
So yeah, I don't know where these guys did. Like I said, I did this a couple of nights ago. I just Googled it and found
But
it.
there's one in Washington. State.
So certainly it's possible, right? Meaning there are machines that are capable of doing it, but then it's a matter of getting access to those machines. The other stuff, like relaxation and so on, these are more, we can handle these at some point, right? You can just have more sophisticated loadings or whatever else. But is it something that's doable? Yeah, I think it's doable, sure.
What do you think about challenges other than just getting the images?
I think DVC is a problem. The more, the more of these you add in there, the more of the hard particles you put, the more difficult it is to do strain measurements if the only place you can measure strain is in the matrix, right? Which is where the dots are, where the particles, the markers are. That's the biggest challenge for me. So the higher the volume fraction, the less likely will be to make quantitative measurements. The way that we've dealt with that on the 2D side is by increasing magnification considerably. This is kind of like what we did on the surface to look at the damaged process zone in the asphalt concrete, right? So you would increase magnification to, let's say, well, okay, I can maybe look, so this area is primarily green, right, meaning matrix. So I can, if I look into here, I can analyze this and get some strain field here, but it's going to be in isolation. I won't know what will be happening in the rest of the object unless you do some kind of either multi-scale measurement or if you do some kind of tiling or stitching, and that's what we do in 2D. That's precisely the kind of thing that we've done. But I think with the asphalt, we just had a very nice camera, so we didn't need to do this, right? But we don't have these good cameras. We have only small resolution cameras. So what we do is we take high resolution pictures at high magnification of little bits of this, and then we stitch them together and get something that's very, very high resolution. And then we can resolve things in the green areas. I can do that with an optical microscope or even with an SEM, but it's very time consuming to do with a tomograph. We've done it. We've done 3. We've done a scan here, a scan there, and a scan there, and tried to join them. But that's like 5 hours worth of experimentation, right? Not the easiest solution, right? But that is another possibility. I think for me, the biggest challenge is that as you increase volume fraction, it is more difficult to make quantitative strain measurements. And a lot of the stuff that we use have high volume fractions, above 50%.
How about the explosives? Were they, what about the fidelity of the 2D surface strain measurement? Were they satisfied
No,
with the...
not really, no. No, it has been very difficult to validate complex codes with only 2D measurements. That has been a problem, right? So, okay, so what do you do in that respect? So what people have done is destructive type measurements, right? So they cut the thing open and then look at inside. But then it's done, right? You can't load it anymore after that. So that is also a time-consuming process. But the third dimension aspect of trying to validate complex 3D codes to some extent has been done by slicing, internal measurements, cutting the thing open and looking inside of it. But again, it's a observation, right? It's not a strain measurement or anything. That has not been done. There's only a handful of groups that do internal measurements like this, and they're all on microstructures that lend themselves to this, right? They're either made this way or they have a natural pattern that works. That's another problem, right? Getting the pattern in there. But I think with any material that is made in a lab, it could be done, right? I think in asphalt, you make it here, right? So there's a lot of flexibility. If you were to just buy it commercially, that would be a bit more difficult to do that. But all these materials that I showed you, we made them. The electrodes we made in the lab. The polymer, obviously, we made in the lab, and so on. So we have some flexibility there.
Any other questions? I guess that's it.
Okay, thank you.
Thank you.
Thanks very much.
One more time.
Thank you.